B part 6, Exterior Algebra. Now, lecture 9, Gauss theorem in Exterior Algebra. Now, in advanced calculus, in R3, Gauss theorem states partial of the surface dot f dot n ds, n is the unit vector, always pointing outside the closed surface. This is integral on the volume, a divergence of f dv, where here f is f1, f2, and f3, and belongs, that's important here, belongs to the tangents vector space. You see? Now, n is the unit normal. On the boundary of the surface, this is a boundary surface. We denote as partial of V. V is the volume. Now, the left-hand side is a flux across the boundary. See the left-hand side, what we derived in previous lectures. So, the right-hand side is a volume integral of the divergence of F. Now, let this space, okay, this you denote this. Attention now, you see, this is omega, capital omega 2 R3 is the collection of all differential two forms on a 3D Euclidean space. You see, the collection of all, this case, of two forms. Likewise, analogously, you see, omega 3 R3, you just repeat the same words. You see, it's the collection of all differential three forms. You see, this is omega 3, three forms on a 3D Euclidean space. This is a omega 3 R3 and omega 2 R2. Now, let's develop the Gauss theorem in the exterior algebra. Step 1. Associate a differential two form to F, this case. We define the two form omega again. This is a collection, okay? As I said before. You see, this is a two form on R3 associated with F by omega F1 dy dz, F2 dz dx, F3 dx dy. Don't forget, this is analogous to vector k. This is unit vector I. This is unit vector G. You see, there's a connection, okay, to advanced calculus. Now, step 2. Take the exterior differential d omega. Attention, omega is a two forms. D omega is a three form. You see, a collection, okay, of all the three forms in the Euclidean space R3. Now, d omega, okay, is d f1 dy dx dz, wedge dz, f2 dz wedge dx, f3 dz wedge dx. On here, let's see, this y, after is z, after is x. Now, z here, this is x, and this is y. See? That's exactly what I said there. I wrote there. So, now, apply the Leibniz rule, okay? Attention, dy dz, dz wedge dx, dx wedge dy, they are constant. So, the differential, okay, here of f1, you just keep df1 and repeat dy dz. Likewise, the differential of f2 is df2 dz dx and df3 dz dx over here. I don't know why I repeat it here. So this is dx, this is dy. You see? You just permute. After z comes x, after x come y. You see? Thus, in this case, I have df1 dy dz. Let's first, okay, work on this first term over here. You see, df1, okay, is one form. Attention now, f1 is zero form. df1 is one form. The one form dy dz. So this one form, I express df1 as the partial derivative f1 respect to x dx, partial f2 respect to y dy, plus partial f3 respect to dz. See, this one in parentheses is a one form. Outside is a two form. So this here, okay, will combine with dy dz, is over there. You see, then I have dx dy dz. But this case, dy, wedge dy, this will be zero. That's why I didn't repeat over there, because it's zero. Analogously, df2, you see, this is a one form. This is a partial f2 respect to y. In this case, dy dz, okay? And you see, this is dx, okay? X, this will be dx dy dz. You see, for you just to see how clear it is, you see over here, you see, this is the x, this is the x over here. So here is the y, you see, this is the y over here, you see. So these are, in this case you have dy, okay, dz, dx. Now attention, look how simple, okay, look. If I move dy on the second place and on the third place, it will be the same, you see. So I will have, in this case, dx dy dz. You see how easy it is? So see how easy it is, you see. Or if I want, I move dx to the left once and this to the left twice. It remains the same because I have two permutation. That's why I can write dx dy dz, the wedge. So this here, okay, is the tree form. Likewise, the same here, you see, I have dx dy dz. Attention now, see, that's very important. This is dx dy dz, that's dx dy dz. Because I can do the permutation, okay, which two permutation leads to the same, okay, it doesn't change the sign. One permutation change the sign. Okay, if I do two permutation, the sign stays the same. Likewise, df3 dx dy, you see, df3, you have dz over here, so dz dx dy. Look how simple. If I move once, it's minus. If I move twice, it's plus. So it's the same here on this case, okay, dx dy dz. See? It's quite clear. There is no problem. So then we can come from here. I just write the omega, okay? The omega belongs to the tree form because omega belongs to two form. D increases the form by one. So this is a tree form. You just put in parentheses, this is dx dy dz, which is dv. And this is divergence of f. See, this exactly, if I integrate this, it's integrated in the volume, okay? Like I did over here, you see? Integrating the volume, because this is a dv, this divergence. This here is from advanced calculus, okay? So you use the divergence, okay? And d omega, I'll just integrate, okay? Over here, this comes to this one. You see, d omega is exactly this term over here. It's quite easy. So this is the famous Gauss theorem in the exterior algebra. You see, there's a connection to advanced calculus. You see the blue one and the blue one, you compare. This is a Gauss theorem, okay, derived assuming using advanced calculus, you see. So this is a connection between advanced calculus and exterior algebra. It's quite clear. Again, take a piece of paper, copy, and try to understand what I did. You see that it's a straightforward, no problem, no complication, no confusion. That's clear. Okay?